So advancing technology usually goes hand in hand with the research as well as medicine. So with the changing sphere of knowledge, it is important for us to link this upcoming technology uh, with research as well as to enhancing their our practice. So this is an attempt to unveil the future medical research with technology. So let's come to it. In collaboration with medical faculty science and technology, I would like to cordially invite our own through the Premraj, President of the Medical Faculty Science and Technology Community, to initiate this.
Okay, can you hear me at the back? Can you hear me? No. Okay, I'll try to speak loud. I'm Kumuthu. I'm the president of the Medical Faculty Science and Technology Community. And so we are here today to talk about TechMed insights. Thank you for that introduction as well. Uh, so uh, let's start off with so we all know that technology and medicine is intertwined, right? So there's always technologies penetrating into medicine and making it uh, like a very lucrative source of innovations, right? What happens there is when you're doctors, you have to use technology, and therefore you have to be quite aware of those technologies. And if you are keen enough, you can also work on improving or creating new technologies in that way. This is just a slide of 40 years of medtech milestones. Let's go to the next slide. This is a sort of a timeline of innovations that have occurred in medical technology. So 1924 EEG and yeah. So you can see that. So there are many quite important innovations that have come about, and they might be older than you might expect, right? So the pacemaker 1936, right? Dialysis 1943, and so on. Okay, and even now, uh, when we think about those things, we don't really truly understand like those intricate mechanisms, right? How they actually work. So it's always useful for us to know about technology. So since we are talking at the medical faculty research community, let's talk about how this relates to research as well. So what is research? Right, so it's not just the research that we do in the faculty, where that's more of a social sciences type of research, right? We take some qualitative aspects, we quantify them, then we analyze them using statistics, and then we present our results in the form of a report or a paper, right? But actually research is investigating some sort of scientific possibility, right? You have some sort of hypothesis, and you actually work towards finding out if you can realize that or not, right? So in that way, when you uh, dive deep into the tech field, it is a sort of research, and also it results in publications and patents as well. So there are quite a few trends that are coming up uh, during these times. If you can't hear me at the back, can you come forward? Uh-huh. Okay. So quite a few trends, right? I was told to speak specifically about some artificial intelligence related topics, but there are so many other innovations. So, smart electronics and sensors, right? Where you can print those sensors and insert or paste them on the body, and they can take your vital parameters, right? And then advanced biomaterials, okay? Nanotech, of course, genetics, and there's computation modeling as well, where what we do is without actually experimenting on live specimens, we take those parameters and we try to work with them on a computer, right? And by using that, you can quite accurately predict what will happen. For example, this how blood flows through arteries. You can model how the blood flows, and then what happens when you place a stent or something like that. Okay? So these are some of the trends. And next slide, please. So what about what can you do to sort of enter this field, right? So to enter into sort of technological field with relation to medicine, right? So one important thing is you need some background knowledge, because we do bioscience for A levels, so we are not exposed to mathematics. We do physics, but not mathematics. And then it's sort of a, how do you say? I think you guys have experienced that. So the there's sort of a uh, rift between the bio and maths people, right? So we are not sort of exposed to that sort of thing. And even in medicine, we are not exposed to say programming or electronics, AI, which we should be knowing because that's coming up now, right? So some background knowledge which you can easily gain by watching a few YouTube videos. There are many like comprehensive YouTube videos. There are short ones as well. So if you want a brief idea, then you can watch some of those YouTube videos. I think I can recommend a few at the end, some channels, right? And also start reading on whatever interests you, right? If you are interested in technology, you start reading on them, not only on books, right? When you are browsing Facebook, you come across those things, right? Then we all have these sort of fields that we are interested in, right? It's not entirety of medicine. So some specific fields and some specific topics within those fields, some of us are interested in. Okay, uh, that may be a personal experience or something like that. So in that case, you should, I think you should focus on those, because those, if you can enter into those topics, then that's what will give you the most satisfaction. Okay. And also there are many researchers not only in the technological field, right? So even many of the doctors here, the lecturers, they engage in research related to technology, right? You may have seen many of those flyers that are shared. Recently, there was a AI enabled ophthalmography or something workshop, right? Maybe some of you joined that. So even within the faculty, those technological aspects are on the rise, right? So if you want to get involved, right, first thing is there are seniors who have been involved, right? Not only our batch, there have been many seniors in the older batches who have been involved in technology that most people don't know, right? Because the thing is, they have not had any exposure. So I have gotten into contact with some of those people. So like they have a vast amount of knowledge, but they have had no platform to utilize it. Okay, so they have gone off on their own, of course, but if they had a platform within the faculty itself, that would have been advantage for us. Okay? So the next thing is to ask your seniors, right, how do I do this? How do I get involved with this sort of research, right? And I'm sure if you ask some sort of researcher, you email them, say, I am this person, I'm a medical student, I'm interested in these things, right? I'm interested in working on this sort of research. So you should find out a researcher who is involved in the research that you want to be involved in, and then I'm sure most of them will reply favorably to you. Okay, they'll be interested in taking you, maybe not completely, but maybe instructing you on how to proceed. Okay, so I have done that, right? So it, like there's no point in just waiting around, right? If you think you want to do something like that, then you need to look for those opportunities. Just like go out and uh, look for them. Okay. So these are some of the major fears that I think as a medical student uh, you should be aware of, right? So this is sort of like in ascending order. Okay, so programming, networking, that's the coding, right? Computer programming and networking. So that's like to get into the basics of that, it's quite easy, right? There are no code platforms and such, so it's quite easy to get into the basics of that. And but to go into depth, it's hard, right? As with any field, but it's easier to enter. Okay, so there are so if you want, if you like, there's no time to explain all the possible sources where you can get this uh, knowledge. So if you want, you can contact me or Alicia, who did the workshop on programming. So you can gain more information on that. Right. So then data analysis. What I mean here is something beyond the community medicine data analysis, right? Some advanced techniques that you can use, uh, sort of say with analyzing these gene related data. Okay, so there are some advanced techniques which you can use for those things. And so electronics and embedded systems, which is just electronics where you can program them and you can transmit and receive information from them, so that you can use them as like remotely from where you are. Okay, so it's and where it is placed, the meaning of embedded system is where it is placed, it functions on its own. It has its own programming and it functions on its own. Right? So for example, we have say the uh, pulse oximeters, right? So it has its own function. It's a standalone piece of equipment, right? So for example, things like that uh, are falling under this category. So if you have joined our electronics workshop, you would know about those things. So we'll have some workshop in the future as well, right? So say the programming and electronics, it's quite easy to get into. Okay, in depth is quite hard. Uh, right. So then AI and machine learning, it's a very upcoming topic these days, right? You guys are aware of that, with ChatGPT and all. So to learn AI and machine learning, it's a little bit different from the normal programming, but that's also I think easy to get into. Right? So you can get the basic understanding and start building AI models without much background knowledge. But if you really want to get into the meat of it, then you'll have to spend a lot of time on it. Okay. Uh, then of course mathematics and physics, where we model biological systems with mathematical models. Okay. That's I think that's also upcoming topic, because there's more and more sort of an analytical type of research that focuses on the uh, say things that previously we would not consider them quantifiable. Okay, so like there are um, yeah I'll get back to that. Okay. Then there's computation modeling and simulations. So simulations, in the sense, what we're doing here is uh, we are taking a real world scenario and we are trying to create a virtual replica of that, right? So with that, for example, a human body simulator where you can dissect the body, right? Those sort of things exist. uh, so that's what simulations are about. So I think out of these you can easily get into programming, AI, and electronics, right? The rest, I think you need some more interest and more time, right? But of course, if you really want, you do have the time. Okay, I'm saying that with my experience, right? So uh, if that's what you really want, then you can find the time for it. Okay, so right, so if you learn some programming and networking, what are the possibilities that you can go into, right? So of course, app development, right? So there's a multitude of apps that you can make, uh, from simple things to very advanced, right? Integrated with AI. So then the other thing is the hospital information management systems. That it's a database system, which sounds boring when you say it, but it's really important when it comes to hospital. Okay, uh, so NHSL has the system for the radiological things, and LRH has a system. So what what's the importance of this is, it can, on one hand, it's easier for the staff, right? It's easier to integrate all the services in the hospital uh, using HIMS, and the other thing is it generates a lot of data, right? So for example, uh, everyone does blood test. So say some hormone level. Okay, so you test that and you enter the records. Okay, so then after 10 years, right, you have 10 years worth of uh, that specific hormone levels, right, at some time series. Okay, so that is a very important resource that you can analyze to understand that hormone. Okay, so you need to filter out, like if the person has a condition, then the hormone levels will be altered. But if you filter those out, if there are normal people taking those things, then that will give you an idea of how that hormone varies. Like we know how hormones vary in a short time scale, right? So circadian patterns, but there are many other variations that occur on larger time scales. Right? There are things called circannual patterns that vary throughout the year. Okay, so those kinds of things you can analyze with that the data that you did not intend to generate, but it did itself. Okay, so that's sort of what you call big data. right? Medical big data where you don't intend to create that data, right? But people take tests, you enter the results, and at the end of some time span, you have a lot of data points which you can analyze. Right? So that's one of the most important things. And of course, telemedicine, where we can remotely uh, operate with the patient and the doctor, right? And that also incorporates you know remote procedures and remote surgeries and things like that. uh, like data analysis, I won't go much into that. So epidemiological data analysis, right? So when the COVID outbreak occurred, so you can analyze those patterns, and then with those patterns you can identify what are the hotspots, right? What is the latent period of the virus and so on, right? And genetics and genomics, they have a lot of data analysis that I'm not fully aware of to tell you. So but I know that it's a very uh, data analysis rich topic. Okay, right, this we talked about. So biological parameters, uh, we can monitor them in real time, and there's some upcoming technologies like smart electronics. uh, so those, I think you guys are pretty aware of those. So let's go to the next slide. Okay, so this is the big topic, right? So AI and machine learning, I'll talk a bit about that. So these are the main sort of domains of AI and machine learning, right? So there's a huge huge importance to medical imaging, right? Because on one hand, it's difficult to interpret, and it takes time to interpret images. Okay, and computers can do that faster than us, right? Not necessarily more accurately. Okay, but if you train it to proper accuracy, then it can be more time saving, more cost saving as well, right? So any sort of image technically can be analyzed, right? So radiological, of course, and histopathological as well, right? You can even analyze a skin lesion and say if it's cancerous or not. And of course, predictive analytics and personalization. So when you enter specific person's details into a HIMS, and you can track that person's health throughout some time, right? So just like how Facebook recommends you ads, right? You use the same principle, and you can predict what sort of what can happen to this person in the future. And with that, you can personalize the treatment of that person, and sort of work on prevention rather than curing, right? So then of course we have virtual assistants, the large language models. So those can if properly utilized, they can actually supplement or even replace a doctor when if it's a resource poor setting, right? It's, human resource poor, right? uh, then it can actually sort of give the proper medical advice, and it's bad to say replace, right, in the medical faculty. So it won't replace, but it can come up to our level. Okay, so another option is sort of these counseling and all that. So say you have a large language model integrated into an app which looks at your psychological well-being. So if the app detects that you are going into depression or something like that, then a large language model, which can, it can't understand you, but it can mimic that. So it can sort of talk to you, right? So if you like ChatGPT is just words, if you add voice to that, right? If you put a reasonably good human voice to that, then it will sound like your friend, right? So then you can actually counsel people using something like this as well. Okay, and of course drug discovery and development, that's, I don't think you guys would be interested. You can sort of model the active sites and all of the proteins and find out what molecules can bind to those, right? So that's the basic thing. So then AI can analyze those things faster than us. Yeah, so mathematical models of mainly biochemical, hormonal, and genetic pathways, right? If you're interested, you can look into this more. I won't go into that. So yeah, so here some hormonal or biochemical systems are too complex for you to analyze by yourself, right? By human, so you can analyze those computationally, right? And of course, there are other things like structural analysis, so bone structure, right? How the stress is transmitted through a long bone, right? Something like that. And fluid flow, as I mentioned, the blood flow through a artery, and what happens when you do an intervention, right? You do angioplasty or stent, and you simulate that and uh, understand what would have happened when if you do it in real life, right? And of course, molecular interactions, so hormones and biochemical cascades again, and how they would function. Okay, so we are getting into a bit of artificial intelligence now. Okay, so you can wake up now and listen, right? I think people don't really understand what this topic is properly, right? Even I don't. So I'll try to give you a gist of what I understand. So first of all, there's computer science, right? That is what you know is the uh, study related to design and use of computers, right? Everything computer is computer science. And then sort of under that you have data science, which is where you have some methods to extract information from data, right? So we are moving into that domain now, the data analysis domain from computer science, right? So everything under that, artificial intelligence and all that, is data analysis. Okay, so then you come into artificial intelligence where it's so it's basically a program, right? It's capable of mimicking human intelligence. So there are of course debates about whether it's really intelligent or not, right? But it can mimic. So if you chat with chat gpt, then and you say thank you, right? It won't understand what you mean. It will say welcome, but it can't really understand it, right? අර ඇතුලේ තියෙනවනේ අර තේරෙනවා කියන එක ඒක නෑ. හරි? Because what it does is it's taking large volume of data, it's analyzing it, and it's telling you what it learned from that large volume of human interactions. Okay, so uh, then under that we have uh, machine learning and deep learning, which we will go into. Okay, so machine learning, if I explain to you basically, it's sort of maybe some won't agree to this, but it's a sort of glorified data analysis. Okay, so what we do here is in normal data analysis, we look at the data, we choose what we are going to do to it, we do the analysis, right? We get the output and we represent it somehow with a graph or something, right? So here what we do is we write the program so that it will find how to represent the data best by itself. Okay, that's basically what this does, right? So with that, it can analyze a large volume of data and sort of find patterns in it that we won't be able to find, because it's too vast for us to look at it in one go and see the patterns in it. Okay, so that is basically what happens. So what we do is we create that sort of algorithm, right? Uh, in the past, when machine learning was not there, people thought that when you program something, you can't get out of it something more than what you put in. Okay, you can't get like, it's sort of like a violation, right, of a law, because it gives out more than what you put in. You input data, right, and it analyzes it in a way that you would not be able to analyze it, and it gives out something more, right, than what you would expect, right? So what you do is you enter some training data and you run it through the algorithm, right? So within the algorithm, it minimizes its errors. So it's sort of like a feedback algorithm. Okay, at first it's completely blank, it doesn't know anything, right? So you input data, it gives a random output. Then you look at it and you say, this is wrong, right? This should be the correct answer to this is this. Then it looks at the gap between what it thought was the answer and what the real answer is, right? Then it will adjust so that next time it runs through the algorithm, the answer is closer to the real answer, right? So when you do that millions of times, it will get closer and closer and closer to the real answer, right? So then it can become quite accurate at getting that answer. So that's something called supervised learning, where you tell it what the correct answers are, right? That is the most commonly used method uh, in medicine, specifically because we need the algorithm to mimic a doctor, right? So we can't have it doing something on its own, right? So we get an expert and we say chest X-rays, what are the normal ones, what are the abnormal ones, right? So you get a doctor to diagnose that, right? And then you input that data into the model, and then at first it will go randomly, but then slowly and slowly it will start identifying firstly which ones are abnormal, which ones are normal, and secondly what features of the program of the image uh, causes it to be abnormal. For example, you have pleural effusion or consolidation. It can slowly understand that this feature is what enables this image to be abnormal. Right? So with that, it can get closer and closer to medical professional. Right? So usually what we do is we input data, we train it, and then we have another separate set of data where you test the model on. Okay, you test it and you validate it, and then so it's like any software has a life cycle. Okay, it's where you create it, then you test it, right? You test it over and over until it's refined enough for you to deploy it, right? It will almost always never be perfect, right? But you have your standards and you come to the standard and then you deploy it. Okay, so this is a slide about sort of the difference between uh, normal machine learning and deep learning. Okay, so deep learning is so you can see there are two steps in the normal machine learning part, and it's all automated in the deep learning cycle. So usually what happens in machine learning is if you wanted to identify some abnormalities, you have to sort of quantify it and tell what those abnormalities are. For example, here it's ECG. So QRS amplitude, what is the normal amplitude, what does it look like. You can give it the normal wave pattern and say, this is normal, the amplitude is with this many squares, right? A T wave inversion looks like this. So you can tell it uh, what uh, what it should be looking for, right? And then it can use those features that you told it to analyze the ECG strip that you give it. It will compare what you told it and what's on the strip and say it's abnormal or normal, right? In deep learning, you don't have to specify exactly what features you should be looking for. You just have to say whether this ECG is normal or abnormal, and it can sort of find out what those features are by itself, right? And also, it's worth mentioning now that in the most part, you don't get these sorts of algorithms in medical devices. It's I think it's quite difficult to patent a medical device. It has a machine learning or deep learning algorithm because it's the intricate data analysis means that you can't really a human can't explain how the output comes. So you can't get a expert to sort of validate what's happening here, right? So that problem causes difficulty in patenting medical devices which use uh, mainly deep learning, right? So in that case, they will have to sort of quantify what features they are looking for, as in traditional machine learning, and then use that. Because when you automate the whole process, you can't really control what sort of features it is looking for, and there may be biases in the data that you provide. Okay, so that problem is still there. So supervised learning is what I've been talking about, where you give the uh, correct output to the algorithm, and it will work its way to the correct output in repeated cycles. Okay, so there are many types. You don't need to know that. So there are some other types: unsupervised learning and reinforcement learning. Uh, unsupervised learning, you can understand it in a sort of these AI image generators and stuff. That those are like in art, there's no correct answer. So that's more towards the creative side of things, right? But mostly in medicine, it's supervised learning because you need a proper standard. Yeah, we'll skip that. That's a bit theoretical. Okay. Yeah, so this is the main point in machine learning and AI, right? So it all depends on what data you feed it. Okay? So if you input some garbage, it will output some garbage, right? Uh, for example, there's this story that they have tried to identify a sort of fish, right? So a very rare sort of fish. So when fishermen catch that fish, they take a photograph with while holding the fish. Okay, so then they use those photographs to train a machine learning algorithm to detect that fish, right? So in all of those pictures, they hold in the fish. So the tips of their fingers are visible below the fish. Okay, so then all throughout that data set, the fish and the fingers. Okay, so the algorithm learn to look for the fingers, not the fish, because you train it on a picture, right? So you say this is this specific type of fish, this is some other type of fish, and then you give that picture to it. It will say it's fish A or B, and you say it's right or wrong. if it's wrong, it will correct itself, right? So there's no inbuilt security that it will do it correctly, right? That is the main problem with patenting machine learning algorithms with medical devices. Okay, so this thing learn to look for the fingers that are underneath the fish, and then when you take a normal photograph of the fish and try to test the algorithm on it, 0% accurate because it doesn't know what a fish is. It just looking for the fingers. There's no fingers, no fish. Okay, there are many other examples of this, right? Like so, that's a important thing. So these graphs are like if you look at this, these are two sets of data points. Okay, some are dark. That's one type of data. The light ones are some other type of data, and what we need to do is classify them. Okay, so how do you classify it is you draw a line across it. Right? So usually when you're doing normal statistical analysis, you draw either straight line or a sigmoid in the yeah. So logistic regression. Yeah. So in AI, you can sort of separate data points with curves. Right? So in the middle one, right, it's a curve. So at our level, we just use straight line. So we would be doing the first thing, right, underfitting, right? And of course, if you try to overdo it, right, with very complex algorithms, then it will become like too trained to the data set, the training data set, right? So as with the overfitting, right, it's like very closely it's trained to the training data set, right? So if you give a uh, data point which you create yourself, not which is not in the training data set, it can't identify that because it's like too trained to the training data set, right? You call that overfitting, right? That happens if you, it can happen if you like train it like too many times, or if the algorithm is too complex, right? It can happen, right? So then those are some of the problems in AI, right? So you need to get it just right to get a optimal fit, right? So this is like if you are into it, then creating the proper algorithm, right? And then choosing like how many times you train and all that. It's a like whole different research topic, right? There are many researches that are happening to identify what algorithm to use, for this instance, and how to train it, like what are the methods. You can combine methods, right? So it's a lot of research, right? So yeah, this is something I like to show where it's a machine learning algorithm where you can read the electrical activity and reconstruct what the person is thinking, okay? What the person is seeing. Okay? From the occipital cortex, you can get the signals and reconstruct what the person is seeing. So on the top row is the presented images, right? So top left is a teddy bear that is placed in front of the person, and then you read the signals from the visual cortex and you reconstruct what the person is seeing, and you get the, which is sort of a teddy bear, right? So it's quite good. Okay, so these things are happening now. That's like the cutting edge of research, but in our scale, I think we can, if we create a sort of proper environment for that, right? We are very medical students are very useful in data generation, right? We go into the wards, right? You see, you go into the dermatology ward, you see skin lesions, right? You take the photograph. That's a like if all the batches do that, then we'll have a large data set of skin lesions that then we can analyze and train a model, right? And then you can create that. You can create an app. Yeah, you can scan the skin lesion, say if it's whatever, right? Cancerous or not, right? Okay, okay. I got this is the fluid modeling that I was talking about. That's a new result. Right? So you can model how the blood flows across that aneurysm and how the turbulence occurs, right? And that's a stent, I guess. And so how the aneurysm is relieved, you can analyze computation. This is a sort of molecular dynamics where you can identify the complicated 3D structures of proteins and how they interact with each other. You can create these electrostatic maps of it's a charge distribution, so you can create those maps and you can find out where the active sites are, where other molecules can bind, right? And you can aid the drug discovery in this way as well. This is interesting. So this is there are modeling platforms that are research grade, right? So without researching on the heart of a live person, right, you can use these research grade modeling tools to do your research on, say, at whatever scale you want, right? If it's the biochemistry of the heart, you can do your research on that scale on the model because it's research grade. It's fairly accurate when you compare to an actual live specimen. So that's those sort of things. Research grade simulations are available even right now. They are yeah. These are some of the sensors that you can use. So yeah, that's okay. Now I have two of my friends here who will talk about sort of what they did for their electives. There's a separate talk on electives at one, right? Uh, we were actually planning to create a tech-oriented elective session by MFSTC, but we couldn't do that because of professorials and people could make it and all. And so some of us will be presenting at 1 p.m. Right? But I chose two of my friends. One has developed an app, and the other developed a human pulse simulator. Right? So I just thought we can learn something about that. So